All right, let's go ahead and talk about the kinetic molecular theory of gases. And what this theory does is it describes how gas particles behave. And really it describes their motion and how they interact with each other. And so for gases, this theory is based off of 5 assumptions. And so there's 5 assumptions about gases that we're going to be talking about. And what I will say is these 5 assumptions should be really easy to get down, but they're often the things that we forget on the exam. So let's make sure we get these 5 down. I'd maybe put like an asterisk next to these. But they're very straightforward though. But gases consist of large numbers of tiny particles, but they're really far apart relative to their size. And so if you take a sample of gas, the particles are very, very tiny, and there's a lot of them. But the gas is actually mostly empty space because of how far apart they are from each other. So most of the volume of a gas is empty space. You think about the air in the room, most of the air in the room is empty space. Gas particles are in constant rapid random motion, and so they're constantly moving around, and they're going in all directions. They're colliding with each other. When they collide with each other, they transfer energy, and then they either gain velocity or lose velocity, and so they're just bouncing all over the place. Gases, because they're in constant rapid random motion, they possess kinetic energy, which is the energy of motion. All right, so we have to think about them having kinetic energy. Collisions between gas particles and between the walls of the container. So when there's a collision between 2 gas particles, or when a particle collides with the wall of a container, those collisions are said to be elastic. Now what that means is, it means that energy is conserved in the collision. And to give you an example, think about like a super bouncy ball. If you were to drop a super bouncy ball, let's say we drop it from this height, the bouncy ball will not go up to the same height that you dropped it from. It'll go pretty close, but what happened is it'll keep bouncing, and each time it comes up, it's not going to go as high as it went before. And the reason why is because that collision is not completely elastic. There's some energy lost in the collision with the floor. Now with gas particles, what we say is the energy that there is before the collision is equal to the energy after. But I do want to clarify something. A gas particle might have a certain amount of energy because it's going a certain velocity, but after the collision, it might have a different velocity, so it'll have a different amount of energy. And so it's not that each gas particle maintains its kinetic energy, it's that the energy of both gas particles added together will be the same. And so if one loses energy, that's because the other one gained that energy. So an elastic collision is one in which there's no net loss of energy. So again, one might lose energy and one might gain energy, but the net loss is 0. This one is not entirely true. There's a lot of factors that go into this, but we do assume with gases that there are no forces of attraction or repulsion between gas particles. And so as they're going past each other, they don't attract or repel each other. They're just kind of neutral. They just go right past each other. Now the reality is there are some small intermolecular forces, for example, London dispersion forces, and not all gases, there's a lot of gases that do attract each other, but the assumption is that they don't. And the average kinetic energy of gas particles depend on temperature, all right? So the higher the temperature, the more the gas particles are moving. And kinetic energy is solved by this equation here, where it's 1/2 mv squared, so it's mass times velocity squared. And so the 2 variables there are mass and velocity, something to keep in mind. So if you have 2 particles that are going the same velocity, but one has a larger mass, that means it's going to have more kinetic energy. The one with the larger mass will have more kinetic energy because you're multiplying it by a larger number. Now we're going to talk about ideal gases. Ideal gases follow this kinetic molecular theory. Really, ideal gases are an imaginary gas because the reality is, especially with the forces of attraction and repulsion, there's always going to be some small amount of attraction or repulsion. So there's not really any gas that fit into an ideal gas, but there are some that get pretty close. All right, so an ideal gas is one that fits perfectly all the assumptions. Now, some gases are more ideal than others. A real gas is a gas that does not behave completely according to the assumptions. All right, and we'll talk about that more as we go forward, like what does that look like. And one factor involved is how polar the gas is. And so the more polar the molecule is, the gas molecule is, the greater the deviation from an ideal gas behavior. And so we think about how gases behave. If you have a gas molecule that has any sort of polarity, for example, carbon dioxide does have polar bonds. It's not a polar molecule, but it does have polar bonds. What ends up happening is it starts interacting with other carbon dioxide gas particles, and the behavior of it is different. Water vapor is a really great one. If you think about water vapor, water is a very polar molecule, and if it's in its gaseous state, it's definitely not going to interact like an ideal gas because of how polar it is. At lower temperatures and higher pressures, real gases begin to deviate significantly from the kinetic molecular theory. And so if it's the lower temperature you go, and the reason why is because they start to move less, so they start to bump into each other more, they start to interact more. Higher pressure, it's because higher pressure means that the gas particles are colliding with each other more often, there's more collisions, and so the opposite of that is going to be the opposite result. So at high temperatures and low pressures, gases start to behave more ideal. All right, so just a couple terms here. Expansion, all right, so gases do not have a definite shape or volume, all right, so they take on the shape of the container they're in and the volume. And so think about, if you think about this room, if it was like a concealed box and you were to make the room bigger, the gas would fill the room. If you were to make it smaller, the gas would fit in there. And so gases can expand or contract their volume, depending on how big the container is. Also compressibility, gases are very compressible. And you think about like a compressor, there's outside the 600 here, there's this compressor that's always running for Dragon Print Shop, and it makes a psst as you walk by. And it's doing that because it's releasing some of the pressure, and inside of there what's happening is there's a bunch of gas being pumped into that compressor there. And so here's a really great example. Notice how we have 3 particles, and notice how when we make the volume smaller, notice how the particles start to collide more. They're occupying less space, but it's still the same amount of particles. But the point here is that you can actually compress them and expand them there. So fluidity. Gas particles are fluid, meaning they can flow over each other. So because of the attractive forces between gases, insignificant gas particles can easily slide past each other. So just like a liquid can flow, gas particles can flow as well. They can just slide right past each other. And gases have very low density. It's because they're very far apart relative to each other. And so you can even see in there that you think about the container, they're low density because it's mostly empty space. So gas, like if you take a volume of gas, it's mostly empty space, low density. So now we're going to talk about diffusion and effusion. All right, and so the first one is diffusion, and diffusion is the spontaneous mixing of two particles, of two gas particles, really. So we're talking about gases. So when we think about 2 different gases, if we introduce them to each other, there's a spontaneous mixing. And so an example would be if I were to spray some cologne or some, air freshener. Eventually, the air freshener would go in would diffuse throughout the whole room. It won't just be isolated right here. It'll eventually be everywhere because of the spontaneous mixing from the random motion of the different particles. And so here's an example. So as the let's say it's perfume comes out, it's going to evenly mix throughout the whole thing there, and that's diffusion. Now effusion is the process by which gas particles pass through an opening. And so if I were to go into my storeroom over here, close the door, spray some air freshener, that might effuse through the cracks in the door, and you might be able to stand next to the door and smell some of the air freshener. And so this is kind of what it looks like. So as the container is open, the gas will effuse through the opening of the container, and then it'll diffuse in the surroundings. And That's it. So make sure you get those 5 here. And what we're actually going to do is we are going to look at the FET real quick. All right, so let's go ahead and think about the 5 assumptions there. All right, so first off, look at the particles, and I'm going to heat them up so that it just looks, so we can see their motion better. But they're in constant rapid random motion. Notice how the particles, not every particle is going the same velocity. They're all going different velocities, but notice that some of them are going really fast, but when they collide with another particle, it transfers its energy to the other particle. So maybe look at that for a little bit. Try to find one going really fast and then watch it collide. And you'll see that the collisions are, that the energy is conserved within the collision, because if one's going really fast, slams into another particle, and then transfers its energy to that particle, the other particle will be moving faster and the original particle will be moving a little slower. The other thing too is, so temperature is the measure of kinetic energy. So if you heat up the gas here, the gas particles will move faster. So temperature is a measure of that kinetic energy. Now, what I want to do is, I'm going to go back to the original thing here. I want you guys to look at the gas particles as they go past each other. And one of the assumptions is that there's no force of attraction or repulsion. But if you look here, you definitely can see some attraction, because the reality is there is some attraction there. And so this is not behaving like an ideal gas. This is not. Because you can see that there's attraction between those particles, and so it's changing the way it behaves a little bit. If you were to increase this temperature though, and you were to get it hot enough, what ends up happening is that attraction doesn't appear to be as relevant. And so the gas particles still are attracted to each other, but if you were to keep heating it up, it'll eventually happen to where the gas particles are moving fast enough where they do just fly past each other. So at higher temperatures, they do tend to behave more like an ideal gas. And that's, yeah, that's it. So that's how gases behave. Make sure you get those 5 assumptions down. Those are easy points on the exam. If you have any questions, feel free to ask.